Hi guys, this is a galvanometer. Depending on how it is wired up, this galvanometer can be used as an ammeter to measure electric current or a voltmeter to measure voltage. In this video, we want to look at how we can use this galvanometer to measure electric current as an ammeter. So, we are interested in converting a galvanometer to an ammeter. This is a very interesting video and it will be so good for those who studied physics, and even if you don't study physics, it is interesting because I will explain it in the simplest term possible so that everyone can enjoy it. So I want to say to you, please stay to the end of this video and enjoy it as you watch along. Now, how does this galvanometer work? The galvanometer works such that when a small amount of current flows through it, this pointer will swing to detect or the corresponding value of the current or voltage it is measuring. In other words, it works by simply the deflection of the pointer. And it does that deflection when a very small amount of current flows through it. So, if you connect the probes of this galvanometer to an electrical component here, a small amount of current is meant to flow through. And that current will deflect the pointer, and the pointer will create a reading that corresponds to whatever measurement you are taking. The question is, how do you make this galvanometer to read as an ammeter or as a voltmeter? In this video, we'll be concentrating on how to make it work as an ammeter because you need some other components to be connected with it for it to work as an ammeter. However, the manufacturer of this galvanometer will always specify at least two things. One, the maximum current that will have to flow through this galvanometer for you to get a full-scale deflection of this pointer. The manufacturer will give you that value. The manufacturer will also tell you the resistance of this galvanometer. With these two parameters known, you can be able to use this galvanometer, wire it up, and take a measurement of current as an ammeter. And that is what we want to explore. Because in secondary school, physics students are normally asked the question, how can you convert a galvanometer with X amount of current to measure XX amount of current as an ammeter? In this video, I want to demystify, I want to rationalize that principle by making it clear to everyone. So let's take this out and make it a bit simpler. I am just going to represent this galvanometer with a symbol G. So let's call this the galvanometer G that I showed you earlier. It is now simplified for the purpose of the explanation. The manufacturer of this galvanometer has specified that the maximum current that will cause a full-scale deflection is 20 milliampere, and the resistance of this galvanometer is 5 ohms. In other words, in whatever you do, do not allow a current of more than 20 milliampere to flow through this galvanometer, otherwise you will damage it. Now, you want to measure a current of as high as 1000 milliampere. What do? That is where you now come in as a physicist or electronics engineer to determine a way you can wire up this galvanometer so that it can measure up to 1000 milliampere without damaging the galvanometer that requires just 20 milliampere to function. Now, what do? Common sense will tell you that if you are able to divert this current away from this galvanometer, you would have successfully protected it. So, if you connect an external circuit like this with a wire or a conductor at this point and connect the other side of the conductor to this point, what happens? You have successfully created an alternative path to divert this current through so that it does not go and damage your galvanometer. So this is the first attempt. Now, in physics or electricity, this conductor is assumed to have zero resistance. It means it does not resist current, so it is receptive to current to flow through. And one interesting thing about current is that it is it does not like stress. The current will always pass through the point of least resistance. If there is no resistance, the current wants to go there because it does not want stress. So, what happens when you do this? The current flows, gets to this point, and spies what is happening here. And as he's spying it, it sees a 5 ohms resistor, and it says to himself, bro, something is going to resist us here. I wouldn't like to go there. And then the current spies through this path and sees that there is nothing resisting it here. What happens? It gets to this point, abandons this route, and diverts itself through this path to continue its journey. So the current will always flow through the path of least resistance. That way, you have successfully diverted the current away from this galvanometer. But the important question is, does it mean the galvanometer will no longer be doing its work? Because if a current doesn't flow through it, it will not take any measurement. So if you successfully divert all the currents through this point, then what is the use of the galvanometer? That is where another question comes in. What must I do? Think about it. What if you put a small resistance here so that when the 1000 milliampere current is flowing through, the resistance here should be smaller than this so that it can at least push back some of the current and tell it, bro, go through the other way. You can't pass here. That way, you would have successfully allowed a significant amount of the current to pass through, while the small resistance here is able to push some amount of current through this point. That is the idea. So the best way to go about it is to introduce a small resistance. This resistance must be smaller than this one. Otherwise, if the current sees a big resistance here, instead of going through this point, it will decide to go through this point and leave only a small amount to pass through here. So you want to put a small resistance here that is smaller than this, very, very small, so that it is just able to allow about 980 of this current to pass through, while 20 is made to pass through this galvanometer. That way, the galvanometer operates successfully to measure the proportion of the current flowing through it and is also able to be protected by this resistor. The question is, what is the value of this resistor that will just be able to make 980 milliampere flow through this part while driving 20 milliampere to go through this part? You need to do the calculation. That is where your job comes in as a physicist or as an electronics engineer, to determine, to design the value of this resistor that will give us that 20 milliampere that deflects this galvanometer. If you don't know what to do, you get stuck. But in our next video, I am going to do a simple calculation using these figures on how to determine the value of this resistor to achieve a 20 milliampere full-scale deflection of the galvanometer. Let me quickly mention that the name of this resistor that is connected here to divert most of the current in parallel to this galvanometer is called a shunt. A shunt. However, the name is not what is important here. What is important is how to make this galvanometer work. Let me end this video like this. An employer wants to interview two candidates, Mr. A and Mr. B. The employer asks Mr. A, what is the name of this resistor? And Mr. A says it is called a shunt. The employer asked Mr. B, what is the name of this resistor? And Mr. B said, I can't remember the name of the resistor now, but I can make this system work. Guess what? Mr. A was hired because he knows the name, while Mr. B was let to go. Now, an important question is, and a food for thought is, if you are an employer, are you looking for a candidate that knows the name or a candidate that can make it work? Thank you for watching this video.